All right, today we're talking about something pretty cool, remapping risk. We're going to explore how a breakthrough in data modeling is totally changing the game for tracking diseases in a world that, let's be honest, never stands still. Let's dive right in. Our story kicks off in Jakarta, the massive capital of Indonesia. And here, you've got these two invisible threats that are just colliding. It's a perfect storm of a public health crisis and a major environmental problem. So first up, you've got the health crisis. Between just 2014 and 2020, Jakarta reported over 84,000, that's 84,651 new cases of tuberculosis. I mean, for an airborne disease, that number is a huge ongoing threat to millions of people. And then, on top of that, there's the second threat, the air itself. So that brings us to the big puzzle. You've got disease hotspots that pop up and move, and you've got pollution levels that change all the time. So how on earth do you get an accurate picture of what's going on? How do you map a problem when the map itself keeps changing under your feet?
To get to the really cool solution, we first have to understand what was broken, and it all comes down to a fundamental flaw in the old maps we used to use for this kind of thing.
Okay, so the fancy term for all this is spatiotemporal modeling. I know, it's a mouthful, but all it really means is tracking patterns across space, like different city districts, and over time. You're not just taking a single snapshot. You're basically making a movie to see how things change. Now, at the heart of these models is something we can call a map of influence. It basically shows how connected different neighborhoods are to each other. But here is the huge, glaring problem with the traditional models. They treated this map like it was carved in stone. They just assumed the connections between places would never, ever change, which, when you think about it, is kind of nuts, right? Yeah, check this out. That old fixed model on the left, it's like trying to navigate today's rush hour traffic using a paper map from 1995. It's just hopelessly out of date. But the adaptive model on the right, that's your GPS. It's live. It's constantly updating, showing you how things actually are right now as connections between areas get stronger or weaker. So you can see why scientists are like, okay, we clearly need a much smarter tool for this job, one that can actually keep up with how the real world works. And this is it. This is the breakthrough. It's a model with a map of influence that can literally redraw itself. Every single year, it looks at the new data and recalculates the connections, capturing how disease clusters are actually evolving on the ground. It's a map that learns. Of course, having a shiny new tool is great and all, but you have to prove it actually works, right? So before they unleashed it on the real-world Jakarta data, the researchers had to put it through a serious virtual stress test. Which brings us to the million-dollar question, doesn't it? I mean, it sounds way better in theory, but does this adaptive approach actually give you better predictions when it really counts? To find out, they used a super powerful technique called a Monte Carlo simulation. The easiest way to think about this is like a virtual lab. They created thousands of different imaginary scenarios to see which model could consistently figure out what was going on. It was a head-to-head competition. And the results? Whoa, they weren't even close. I mean, just look at this chart. That huge bar on the left, that's the prediction error for the old fixed model. It was terrible. But then look at the tiny little bar for the new adaptive model. It stayed accurate no matter what they threw at it. The test was over. The smarter tool won, hands down. Okay, so now they had a proven winner, a much more powerful tool. It was finally time to go back to the original mystery. What was really happening with TB and air pollution in Jakarta? They zeroed in on these 5 key air pollutants, tracking their levels all across the city year after year, from 2014 to 2020. They took all that pollution data, all the TB case numbers, and they fed the whole thing into their new adaptive model. And what came out the other side was a crystal clear, statistically significant link. And it turned out, while all 5 pollutants were part of the problem, 2 of them were the real villains of the story. First up, the biggest offender, nitrogen dioxide, or NO2. Now get this. The model showed that for every tiny increase in NO2, we're talking just 1 microgram per cubic meter, the risk of contracting tuberculosis jumped by a staggering 21.17%. That is a massive effect. And the second biggest culprit was sulfur dioxide, or SO2. Same story here. A similar tiny increase in this pollutant was linked to a 13.20% rise in TB risk. So for the very first time, researchers had a clear, quantifiable link showing exactly how the city's air was making its people sick.
And this is where you really see the power of that adaptive model. Just watch this timeline. Okay, so in 2014, you see these scattered pockets of high risk. A little here, a little there, but watch what happens. By 2017, the model shows those spots are starting to connect, to merge and form dangerous clusters, especially over in the east. Then, fast forward to 2020, and the entire city map is red. The threat wasn't just growing, it was consolidating. So, what's the big takeaway here? What does all this mean beyond just Jakarta? Well, this research has some really profound implications for public health pretty much everywhere. It really all boils down to one simple idea. Models that can adapt to a changing world give us a much clearer picture of the future. And this isn't just an academic exercise. It means health officials can see where risks are emerging, send help where it's needed most, and make smarter, faster decisions that actually save lives. And that leaves us with a pretty exciting thought to end on. This technology gives us the power to create these living, breathing maps of risk for diseases like TB. So if we can do that, what else is possible? From tracking the impacts of climate change to predicting economic shifts, you have to wonder, what other huge, complex problems could we solve next?